Welcome! In this session, we'll dive into LeetCode problem number 590, N-ary tree postorder traversal. This problem focuses on traversing an N-ary tree in postorder and returning the node's values. Postorder traversal is widely used in tree-based algorithms, making it an essential skill for technical interviews. Let's get started. In this problem, we are tasked with performing a postorder traversal on an N-ary tree. In an N-ary tree, each node can have anywhere from 0 to n children. Postorder traversal follows a specific order. First, you visit all the children of a node from left to right, and only after that do you visit the node itself. The output will be a list of integers representing the values of the nodes in this traversal order. The input to the problem includes the root of the N-ary tree, which is either a node object or null if the tree is empty. Each node object contains two attributes, val, which is the value of the node, and children, which is a list of child nodes. The output format expects us to return a list of integers representing the traversal order. Let's take a look at an example to understand this problem better. Here, the input is a tree represented as root equals 1, null 3, 2, 4, null 5, 6. The tree structure is visualized with the root node, 1, having 3 children, 3, 2, and 4, node 3 itself has 2 children, 5 and 6. The postorder traversal for this tree would result in the output 5, 6, 3, 2, 4, 1. This is achieved by first traversing the children of node 3, then visiting node 3 itself, followed by nodes 2 and 4, and finally visiting the root node, 1. Looking more closely at the explanation, we start with the root node, 1. The traversal first visits its children, nodes 3, 2, and 4. For node 3, we then visit its children, 5 and 6, before visiting node 3 itself. Nodes 2 and 4 don't have any children, so they are visited directly. Finally, after all children of node 1 have been visited, we visit node 1 itself. This step-by-step process ensures that the traversal adheres to the postorder rules, visiting children first and the parent node last. In another example, the input tree is root equals 1, null 2, 3, 4, null 5, and null 6, 7. Here, the tree structure shows the root node 1 with 3 children, 2, 3, and 4. Node 3 has a single child, 5, and node 5 itself has 2 children, 6 and 7. The postorder traversal output for this tree is 2, 6, 7, 5, 3, 4, 1. We achieve this by visiting node 2 directly first, as it has no children, then moving to node 3 and traversing its child, 5. For node 5, we visit its children, 6 and 7, followed by node 5 itself. After that, we visit node 3, then node 4, and finally the root node, 1. There are a few edge cases to keep in mind for this problem. If the tree is empty, meaning the root is null, the output should simply be an empty list. If the tree consists of only a single node, such as root equals 1, the output will be a list containing just that node's value, 1. For deep trees, where the height approaches the constraint of 1000, it's important to ensure the traversal handles recursion or iteration efficiently without exceeding limits. Similarly, in cases of wide trees, where nodes have a very large number of children, close to 10,000, the solution must be able to handle the traversal without performance bottlenecks. These scenarios test the robustness of the implementation. To tackle problem number 590, N-ary tree postorder traversal, our goal is to visit the nodes of an N-ary tree in postorder, which means processing all the children of a node first, followed by the node itself. Let's start by considering the recursive approach. This method is particularly intuitive because it directly mirrors the definition of postorder traversal. For each node, we recursively traverse all of its children, ensuring that their values are added to the result before we process the current node. The steps are straightforward. We begin at the root, traverse each child in postorder, and finally append the root's value. From a complexity standpoint, this approach is efficient, with a time complexity of O(n), as we visit each node exactly once. The space complexity is O(h), where h is the height of the tree, due to the space required for the recursive call stack. While simple and elegant, one drawback is the potential for stack overflow if the tree is very deep. To address this, we also considered an iterative approach using a stack, which we'll now discuss in detail. The iterative approach simulates postorder traversal without recursion, making it a great alternative for avoiding stack overflow. Here's how it works. We use a stack to keep track of nodes yet to be processed. Starting with the root, we push it onto the stack. Then, we repeatedly pop nodes off the stack, add their values to the result, and push their children onto the stack in reverse order. This reversal ensures that the children are processed in the correct sequence for postorder. Finally, once all nodes have been processed, we reverse the result list to achieve the desired postorder sequence. This method has a time complexity of O(n), as each node is processed once, and a space complexity of O(n) in the worst-case scenario, such as when the tree is structured with all nodes as children of the root. The main advantage is that it avoids recursion, eliminating the risk of stack overflow. However, implementing this approach requires additional steps, like reversing the result, which introduces some complexity compared to the recursive method. After evaluating both approaches, we selected the recursive method due to its simplicity and natural alignment with the definition of postorder traversal. The key insight is that recursion inherently matches the traversal requirements: process all children first, then the node itself. This makes the recursive solution clean and easy to understand. While the iterative approach avoids recursion and the associated risk of stack overflow, it adds complexity by requiring the result to be reversed at the end. Additionally, the iterative method doesn't offer significant performance benefits in this case. Since the problem does not impose strict constraints on tree depth, the likelihood of encountering a stack overflow is minimal in practical scenarios. In conclusion, the recursive approach strikes the right balance between simplicity and efficiency, making it the most suitable choice for solving this problem. In this problem, we are tasked with performing a postorder traversal on an N-ary tree. Postorder traversal is a process where, for each node, we visit all its children before visiting the node itself. The final output is a list of node values arranged in this specific order. To achieve this, we can use a recursive approach that leverages the natural structure of recursion to simplify the traversal process. First, we take the root node of the N-ary tree as input. The base case here is straightforward: if the root is none, meaning the tree is empty, we simply return an empty list since there are no nodes to traverse. Then, we define a helper function called postorder_traverse to handle the recursive traversal. For each node, we initialize an empty list to collect the postorder values of its subtree. We process all of the node's children recursively, appending their results to this list. Finally, after all the children have been processed, we append the current node's value to the result, reflecting the postorder sequence, and return the list. Once we have defined the helper function, we call it on the root node and return the result, completing the traversal. Now, let's delve into some key insights about this recursive approach. Postorder traversal inherently follows the pattern of processing all children first, from left to right, and then the current node. This recursive method mirrors this pattern naturally. The recursive call stack is crucial here, as it handles both the traversal order and the backtracking needed for the algorithm to work. Each recursive call deals with processing one node and its subtree, and when the recursion unwinds, the nodes are appended in the correct postorder sequence. In terms of efficiency, the algorithm is highly optimal. Each node is visited exactly once, and each edge in the tree is traversed exactly once, giving us a time complexity of O(n), where n is the total number of nodes in the tree. The space complexity is O(h), where h is the height of the tree, because the recursive call stack grows with the depth of the tree. To implement the algorithm, we rely on two main data structures. First, we use a result list to store the node values in postorder sequence. This list is updated as we traverse the tree, with values being appended only after all children of a node have been processed. Second, the recursive call stack plays a central role in managing traversal order and backtracking. Each stack frame corresponds to a specific node being processed, ensuring the correct sequence is followed. Now, let's address potential edge cases. If the input tree is empty, meaning the root is none, the function should return an empty list immediately. For a tree with just a single node, the result should be a list containing only that node's value. Finally, in the case of unbalanced trees, such as a tree where all children are on one side, the algorithm still handles this naturally by recursively processing each subtree in the correct order. Unbalanced trees, whether left-skewed or right-skewed, are handled seamlessly because the recursive method processes each node and its children independently. This ensures that the traversal remains accurate regardless of the tree's shape. Let's discuss some key operations involved in the algorithm. First, the recursive traversal processes one node and its children at a time, ensuring that each subtree is visited in postorder. Second, list concatenation is used to combine the results returned by recursive calls for each child node, preserving the correct sequence. Finally, the current node's value is appended to the result after all its children have been processed, completing the postorder sequence for that subtree. With these operations in place, we can implement the algorithm in Python. We start by defining a node class to represent the N-ary tree structure. The postorder function begins with a base case. If the root is none, we return an empty list. Then, we define the recursive helper function postorder_traverse to handle the traversal process. Within the postorder_traverse function, we iterate over all the children of the current node, calling the function recursively for each child. The results of these recursive calls are extended into the result list, ensuring that the children's values are captured in postorder. Once all children have been processed, we append the current node's value to the result list. This step ensures that the node itself is added only after its children have been fully traversed. Finally, the result list is returned for each call. To complete the traversal, the postorder function calls postorder_traverse on the root node and returns the final result. In terms of complexity, the algorithm is efficient. The time complexity is O(n), since each node and edge is visited exactly once. The space complexity is O(h), due to the recursive call stack, where h represents the height of the tree. This implementation is both concise and effective, making it well suited for the problem. Let's walk through an example to solidify our understanding. Consider the input tree where the root node is 1, and it has 3 children, 3, 2, and 4. Node 3 itself has 2 children, 5 and 6. The traversal starts at the root 1, and we process its children one by one. First, we visit node 3 and process its children. Node 5 is visited and added to the result since it has no children. Similarly, node 6 is visited and appended. After processing both children, we append the value of node 3. Next, we move to node 2, which has no children, so we append its value directly. The same happens for node 4. Finally, after processing all the children of the root, we append the root's value, 1. The resulting postorder traversal is 5, 6, 3, 2, 4, 1. This example demonstrates how the algorithm processes each node and its subtree systematically to achieve the correct order. This Python implementation solves the LeetCode problem 590, N-ary tree postorder traversal. Let's break it down step by step. 1. Node class. The node class is provided as part of the problem definition. It represents a node in an N-ary tree. Each node has a val for the value and children for its list of child nodes. If no children are provided, it defaults to an empty list. 2. Solution class. The solution class contains the postorder method, which performs the postorder traversal of the N-ary tree. 3. Base case. The first thing we check in the postorder method is whether the root is none. If the tree is empty, we return an empty list as the result. 4. Result list. We initialize an empty list result to store the postorder traversal of the tree. 5. Recursive traversal function. The inner traverse function performs the depth-first traversal recursively. For each node, it iterates through all its children and recursively calls traverse on each child. After processing all the children, appends the current node's value to the result list. This ensures that all children are visited before the current node, which is the essence of the postorder traversal. 6. Start traversal. We call the traverse function with the root node to begin the traversal. 7. Return result. Once the traversal is complete, the result list contains the postorder traversal of the tree, and we return it. #### key points. The recursive function ensures that nodes are processed in the correct order for postorder traversal, children first, then the node itself. The solution handles edge cases like an empty tree, root is none, by returning an empty list immediately. This implementation is efficient and concise, with a time complexity of O(n), where n is the number of nodes in the tree, since each node is visited exactly once. The space complexity is O(h), where h is the height of the tree, due to the recursive call stack. Here, we start by defining the structure of an N-ary tree node using a class called node. Each node has an integer value, val, and a list of child nodes, children. We provide three constructors, a default constructor, one that initializes only the value, and another that sets both the value and the list of children. This gives us flexibility when creating tree nodes. Next, we define the solution class, which contains the postorder method. This method will handle the traversal of the N-ary tree. First, we initialize an empty list called result to store the traversal output. If the root node is null, we simply return this empty list. This is a safeguard to handle edge cases where the input tree might be empty. Now, we invoke a recursive helper function named traverse to perform the actual postorder traversal. The traverse function takes the current node and the result list as parameters. Inside this function, we iterate over each child of the current node and recursively call traverse on them, ensuring that we visit all the children before processing the current node itself. Once all children have been processed, we add the value of the current node to the result list. This adheres to the postorder traversal principle, where we visit children first and then the node itself. Finally, the postorder method returns the result list, which contains the values of the nodes in the correct postorder sequence. In this example, we start with the simplest possible case, a single node tree where the root node has a value of 1 and no children. When the postorder method is called, it first checks if the root is null. Since it's not, we initialize an empty list called result to store the traversal output. Next, the traverse function is invoked with the root node. Inside the traverse function, we attempt to iterate over the children of the node, but since there are no children for this node, the loop is skipped. The value of the root node, which is 1, is then added to the result list. Finally, the method returns the contents of the result list, which is 1. This demonstrates that for a single node tree, the postorder traversal is simply the value of the root node itself. Now, we examine a more complex tree with multiple levels. The root node has a value of 1 and 2 children, node 2 and node 3. Node 3 further has 2 children, nodes 4 and 5. The postorder method is called with the root node, and as before, we initialize an empty result list. The traverse function is then called with the root node. The function begins iterating over the children of the root. The first child, node 2, is encountered and passed to the traverse function. Since node 2 has no children, its value is added directly to the result list. This is the first step in building the postorder traversal result. After processing node 2, the next child of the root, node 3, is passed to the traverse function. Node 3 has 2 children, so the function begins iterating over them. The first child, node 4, is processed. Since node 4 has no children, its value is added to the result list, which now becomes 2, 4. The second child of node 3, node 5, is then processed in the same way. Its value is added to result, resulting in 2, 4, 5. After both children of node 3 are processed, the value of node 3 is added to the list, making it 2, 4, 5, 3. Finally, after all children of the root node are processed, the root node's value, 1, is added to the list. The final result of the traversal is 2, 4, 5, 3, 1, which correctly reflects the postorder traversal order. In the case of an empty tree, the root is none. When the postorder method is called, it immediately checks if the root is null. Since it is, the method skips all further processing and directly returns an empty list. This straightforward handling of the edge case ensures that no unnecessary computations occur when there are no nodes in the tree. The output in this case is simply. This demonstrates how the solution gracefully handles an edge case where no traversal is required. By using this approach, we can efficiently traverse any N-ary tree in postorder. The key insights are that the traversal processes all children of a node before adding the node's value to the result, and the recursive nature of the traverse function allows for a depth-first exploration of the tree. The method also handles edge cases like empty trees and single-node trees efficiently. With a time complexity of O(n), where n is the number of nodes, and a space complexity of O(h), where h is the height of the tree, this solution is both optimal and robust for postorder traversal of N-ary trees. The time complexity for the N-ary tree postorder traversal algorithm is O(n), where n represents the total number of nodes in the tree. This is because each node is visited exactly once during the traversal. Specifically, the recursive traverse function is called for each node, and within that call, we iterate through the node's children only once. Additionally, for every node, we perform a constant time operation, O1, to append its value to the result list. Since we are visiting all n nodes and performing O1 work per node, the total time complexity is O(n) multiplied by O1, which simplifies to O(n). This ensures that the algorithm is efficient and processes the entire tree in linear time. The space complexity of the algorithm is influenced by two main factors. First, the recursive call stack, which depends on the depth of the recursion. This depth corresponds to the height of the tree, which varies based on the tree's structure. In the worst-case scenario, such as a completely skewed tree, the recursion depth can reach n, where n is the total number of nodes, leading to a space complexity of O(n). In the best-case scenario of a balanced tree, where the children are evenly distributed, the recursion depth is proportional to log n. The second factor is the result list, which stores the values of all nodes. Since this list grows linearly with the number of nodes, it contributes an additional O(n) to the space complexity. Combining these, the overall space complexity remains O(n), as the result list dominates in both the best and worst cases. In terms of best, average, and worst case analysis, the time complexity is consistently O(n), regardless of the tree's structure, because every node must be visited exactly once. For space complexity, the best case occurs when the tree is perfectly balanced, minimizing recursion depth to log n, but the result list still requires O(n), making the total space complexity O(n). In the worst case, with a highly skewed tree, the recursion depth reaches n, and the space complexity remains O(n), due to both the call stack and the result list. Comparing this implementation to alternatives, there is no brute force or shortcut approach, as postorder traversal inherently requires processing all nodes. Therefore, this algorithm is both optimal and efficient. Mathematically, the recurrence relation for time complexity is T(n) equals sigma T, C_i, plus O(1), where C_i represents the sizes of the children's subtrees. Since the sum of all child nodes equals n1, this simplifies to T(n) equals O(n). For space usage, the recursive stack depth depends on the tree's height, up to n in the worst case, and the result list contributes O(n), resulting in a total space complexity of O(n). When working on N-ary tree postorder traversal, there are a few common mistakes to watch out for. One frequent issue is confusing postorder with preorder traversal. Remember, in postorder, all the children of a node must be visited before the node itself. Processing the node too early, before its children, leads to a preorder-like traversal. To fix this, always ensure the node value is added to the result after all its children have been traversed recursively. Another common error is mismanaging the recursive base case. If you don't handle nodes without children properly, it can cause infinite recursion or null pointer exceptions. To avoid this, explicitly check if the node's list of children is empty before attempting recursion. Additionally, edge cases like an empty tree or a single node tree are easy to overlook. Failing to account for these can lead to incorrect outputs. Always include checks for cases like root == null and test your code with minimal inputs. Lastly, if you're implementing an iterative solution, be cautious about the order of results. Iterative postorder traversal tends to add nodes in reverse order, so forgetting to reverse the result list at the end can lead to errors. Always make sure to reverse the list before returning it when using this approach. Another important consideration is understanding the impact of tree depth, especially in interview settings. Deep trees can cause stack overflow when using recursion, and some candidates forget to highlight this risk. Discussing iterative alternatives in such cases can demonstrate a deeper understanding of the problem. Looking at the broader picture, there are key insights to keep in mind for interviews. First, postorder traversal is a type of depth-first search, or DFS, so mentioning this connection can emphasize your grasp of traversal techniques. Second, explain that recursion inherently uses the call stack, which is conceptually similar to managing a stack manually in an iterative approach. This demonstrates your ability to connect different implementation methods. Third, if you're using an iterative approach, make sure to explain why reversing the result list is necessary and how it ensures the order aligns with postorder requirements. Finally, be prepared to discuss the time complexity, which is O(n), and the space complexity, which is O(h), where h is the height of the tree. Highlight the trade-offs between the recursive and iterative methods, such as simplicity versus safety for deep trees. Postorder traversal is closely related to several other traversal problems, and understanding these connections can help you build a stronger foundation. For example, LeetCode problem number 589 covers N-ary tree preorder traversal, which is similar but requires visiting the node before its children. Another related problem is LeetCode number 94, which focuses on binary tree in-order traversal. Here, the traversal visits the left child, then the node, and finally the right child, illustrating a different order compared to postorder. Additionally, LeetCode number 145 deals with binary tree postorder traversal, which is a simpler version of the N-ary tree postorder problem due to the binary tree's limited branching structure. Lastly, LeetCode number 102 explores binary tree level order traversal, which uses breadth-first search instead of depth-first search. This problem provides a contrasting perspective on tree traversal techniques and can help you see how different methods apply to various scenarios. There are several approaches to solving N-ary tree postorder traversal, each with its own trade-offs. The recursive approach is often the most straightforward and intuitive. It leverages the call stack to manage the traversal order naturally, making the implementation clean and easy to understand. However, it has the disadvantage of being prone to stack overflow when dealing with very deep trees. On the other hand, the iterative approach, which uses an explicit stack, avoids this limitation and is safer for deep trees. However, it requires careful handling of the result list, including reversing it at the end to ensure the correct postorder sequence. This added complexity can make the iterative solution harder to implement correctly. Lastly, there's the Morris traversal technique, which is efficient for binary trees as it operates in O1 space. However, it's not commonly used for N-ary trees due to their more complex structure. Understanding these alternatives and their trade-offs allows you to choose the most appropriate method based on the problem requirements and constraints. Great job! To summarize, we explored the N-ary tree postorder traversal problem, discussing both recursive and iterative approaches. We reviewed the time and space complexities and key takeaways for solving similar problems. Don't forget to practice and apply these concepts in other tree-based challenges. Thanks for joining, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!